So let's talk about a technique called implicit differentiation. So, what does this apply to? Well, let's talk about a circle. So suppose we have a circle of radius 1. So just this circle here. And of course, we can write an equation for this circle. All points on this circle of radius 1 satisfy the equation x squared plus y squared is equal to 1. But now we can do the following. Well, this is a curve like any other. Well, maybe it makes sense to take a point on this curve and try to draw a tangent line to it. Or a point here and try to draw a tangent line here. Well, I haven't written down any definitions for you, no limits, no anything, but I don't think that anyone is going to fundamentally disagree with the fact that this line is really what the tangent line to the circle should be here, this here, and so on and so forth. So I think we have a pretty unambiguous, intuitive notion about what a tangent line should be here. The question is, how do we find it? Well, in this case, yes, you could solve for y equals and get two different functions, one for the top, one for the bottom, from the two different square roots. But let's not do that, because I'm giving you this technique, and I'm using this simple example of the circle because it's nice to look at, but let's just talk about how this technique is going to work in general, and then as we go on, we'll do some other examples. So what does this word implicit mean? This word implicit means is that even though this isn't in the y equals form, it sort of implicitly defines a function, because if x and y play this little game with one another, at least at various points along the graph of this relation, you can sort of write it out as a function. So, if you will, this relation implicitly defines a function. So we're going to talk about how implicit differentiation works and how we can find a technique to not solve for y, but nonetheless find a way to solve for dy by dx, the derivative of y in x, which will spit out the slopes of these tangent lines. Okay, so how we do this is, so imagine y is equal to f at x. So we've already talked about this. This equation implicitly defines a function, if you will. So we can talk about the derivative of this function, and we can just give this a name, dy by dx. And now, what do we know? We know that x squared plus y squared is equal to 1. So what is this? This is an equality of functions. This left-hand side is a function of x, because we're imagining that x is of course a function of x, so x squared is a function of x. But if y is also a function of x, then y squared is a function of x. And okay, on the other side, 1, it's a constant function, which we can still think of as a function of x. So what we can do is we can differentiate both sides. If these two functions are equal, their derivatives must be equal. So let's write that out. Well, what's the derivative of x squared? It's 2x. What's the derivative of y squared? Well, this is a chain rule thing. The outside function is squaring, the inside function is just y, so the derivative of this guy is 2y times the derivative of y, which we're just calling dy by dx. And this has to be equal to, well, what's the derivative of 1? It's 0. This gives us an equation involving dy by dx, but of course we can move things around and solve for it to get that dy by dx is equal to negative x over y. Alright, let's try this out. So what's a point on the circle? Well, one point on the circle is, say, 1 over root 2, 1 over root 2. That's definitely a point that satisfies this equation. And that's just going to be this point right here. And if you think about what the tangent line at this point right here is going to be, well, that sort of looks like a nice, perfect slope of exactly -1, because it just hits this point that's just 45 degrees up on the circle. The tangent line should be perpendicular to this line, so this should be a perfect slope -1 line just going down like this. But indeed, if we plug this into our formula, that is what we're going to get. So if we take dy by dx at this point here, well, what we do is we just plug in these two numbers as x and y, and we're going to get -1 over root 2 divided by 1 over root 2, which is of course going to be equal to -1. And we could try this out with some other points, and it's going to work. It's going to give us the tangent line we'd want, and indeed, this is how this thing is going to work. So what we're going to do now is we're going to do a couple more examples with this, one to deal with inverse functions, and then another where we're going to have a more complicated curve where it's a little harder to solve for what y is, or at least if we did, it would be more complicated to work with. And the point here is that even though this example is simple, this technique is going to work with any example whatsoever. So let's work through some more. Okay, so this is the example part of video 8 on implicit differentiation. Okay, so as promised, one thing that you can do with this is you can use this technique of implicit differentiation to compute the derivative of inverse functions. So let's suppose we have y is equal to ln x, and we want to find the derivative of what this guy is. So what can we do? Well, obviously we can't just differentiate things, that's circular. What if we didn't know the derivative of the logarithm? How could we figure it out? Well, what we could do is, of course, we could take e to both of these sides. So since we have that y is equal to ln x, we would have to have that e to the y is equal to e to the ln x. But again, e to the ln x is just equal to x. But now, can we differentiate this? The answer is yes. We can implicitly differentiate this because we know how to differentiate x, and we know how to differentiate e to the x. So now, by the chain rule, we can use implicit differentiation and say that since e to the y is equal to x, we can claim that, well, how do you differentiate this guy? The inside guy, u, is y, so the derivative of this thing is e to the y times dy by dx, and this thing now has to be the derivative in x of x, which is 1. So we have that dy by dx is 1 over e to the y. Now, this is a correct statement, don't get me wrong, but it's not a helpful statement yet because it doesn't tell us what the derivative is in terms of x. But note that we computed here that e to the y is in fact equal to x. So we get that dy by dx is therefore equal to 1 over x, which we saw before. So this is another way to work that out. So now, and indeed, this function still, if you wanted to solve for y, you could still do it. I picked this example because it's nonetheless a pretty function. Let's talk about an example of a curve. Y squared is equal to x cubed minus 2x. So what does this curve look like? Well, this curve is sort of interesting. It's called an elliptic curve, actually, and it has two pieces. It has some guy here and another guy here. So it has a fun little graph. And one could ask then, well, you can quickly check the point 2, 2 is on this curve. Why? Well, because if you take 2 squared, that's going to give you 4. If you take 2 cubed, that's going to give you 8, and 2 times 2 is going to be 4, so yes, 4 is equal to 8 minus 4, which is 4. So we're good. 2, 2 is a point on the curve. Let's find out what the tangent line, what the slope of the tangent line is at this point. So indeed, all we have to do is do this same implicit differentiation process. Let's differentiate both sides here using implicit differentiation. Again, we get that the derivative of y squared by the chain rule is 2y dy by dx. And the right-hand side is just a polynomial, so its derivative is just 3x squared minus 2, which gives us that dy by dx is just 3x squared minus 2 all over 2y. So now, if we plug this in at 2, 2, well, what do we get? Well, let's just plug in 2 for x and 2 for y. We're going to get 3 times 2 squared, which is 4, minus 2, all over 2 times 2. And this is going to be 12 minus 2, which is 10, over 4. So this is going to be 5 over 2. And indeed, it's not like I drew the best picture in the universe here, but that looks about like a line with slope 5 over 2 to me. So I'm going to say it probably worked out. So indeed, this is how we can use this tool. It's really not too bad. The sky's the limit in terms of how complicated these sorts of expressions can be, but if you know how to differentiate complicated functions, you'll be able to handle even complicated cases as well.